In this video, we're going to be looking at solutions to simultaneous linear equations. And specifically, these are questions which ask you for a specific number of solutions, and therefore you have to find values of a variable to satisfy the number of solutions. So this is when you have two equations, so linear, so it means you can put them in this form or rearrange them to this form. We have y equals mx plus c, then y equals ax plus b, and then there'll be some values in there, but a may be left as just a. And then if it said sort of find a unique solution, so when these two simultaneous equations only give one solution, what are the values of a? And for example, they could be, therefore a is equal to 2, or it could be something more like a is equal to all real numbers apart from 3. As we'll see here, we'll go through it. So it makes a bit more sense once you've sort of seen a few questions, but these just to emphasize they're linear. So that means you can always put them in the form y equals mx plus c. So they have two things, the translation and then the gradient. And we're looking at two of them. So we'll begin with looking at some graphs of, so these are the graphs of linear equations. So there are three different types of graphs we'll go through. So the first is, these are parallel lines and there are no intercepts. So these are no intercepts. And as there's no intercepts, that means there's no solutions when you solve them simultaneously. And these are parallel, but we'll go through them in a sec. So the other two are here where they cross over. So that is a unique solution. So because they're linear, they can only have one intersection. So that's what we're going to call sort of a unique solution, or one solution to the simultaneous equation. Then the third one is when they're the exact same line. So when they're exactly the same line, then every single point is a solution. So there'll be infinitely many solutions. Now, before I was talking about how the linear line can be represented by y equals mx plus c. Now it can be other forms, but you can always bring it back to this form. And here there are two key features. So you have the gradient, and then here you have the translation. Now, because it's a linear line, the x and y translations just combine into one translation. So we can just call that the plus c, or if c is negative, like the minus c. So the gradient, and we have the translation. So looking at these graphs, so here the no intercept and the no solutions. So first thing is, for this to occur, the gradients have to be the same. That's because they are parallel. So looking at m, they have to be the same. And then the plus or minus c, so the translations must be different. And why is that the case? Well, m has to be the same because they never intercept. If they were different, then eventually they would intercept at some point. So that's why they're the same. But why does the plus c's have to be different? Well, if the plus c's are the same, then we have both things as being the same. If that's the case, then they're going to be the exact same line. And if they're the exact same line, there will be infinitely many solutions. So this is for no solutions, and they have these two conditions where the gradients are the same and the plus c's are different. What about here, where you have a unique solution? Well, the gradients have to be different, because if they're the same, they'll never intercept. And then the plus c's, so the plus or minus c's, it doesn't matter. That's quite important. It doesn't matter. So even if the plus c's are the same, this will mean there's just one unique solution. So the translation won't affect it, because if it goes up or down, the intercept point will change, but it'll still be one unique solution or one intercept. So for the third case, infinitely many solutions, then they're going to be the same line. For that to occur, the gradients have to be the same, and also the translation has to be the same. So the plus c has to be the same. So the way that I solve these equations is I rearrange to get it in the form of y equals ax plus b and y equals cx plus d. So these are the two equations. So they give it in a different form, then I rearrange. So I have the gradient, then I have the translation here. Then depending on what they want, I let them equal or not equal. So let's say I wanted infinitely many solutions. So if I want infinite solutions, I think first about the gradient. Now the gradient has to be the same. Therefore, A is equal to C. Then I think about the plus or minus C, so the translation. And then the translation has to be different. So that means B cannot equal D. Now as there's no numbers at the moment, this seems a bit confusing. Once you see a question, this will make a lot more sense. Then if I was looking at something like a unique solution, I would let the gradients not equal. So I think about always like the gradient. So the gradient's not equal, translation, it doesn't matter. So translations can equal anything. But the gradient would have to not be equal. So looking at this example, we have find the values of m and a for the simultaneous linear equations y equals 5x minus 2 and y equals mx plus a. So firstly, they're in the form y equals mx plus c, so we don't have to worry about rearranging them. But now we want to look at for no solutions. So we have to look at the two different aspects, the gradient and the translation. So firstly, looking at the gradient, we want the gradients to be the same because for no solutions. So if you remember graphically, they have to be the same so they never intercept. So if they're the same, m must equal 5. It's because the gradient of one must equal the gradient of the other one. Now looking at plus or minus c, they have to be different. So that means a cannot equal -2, but it can be any other value. So therefore, for no solutions, m must equal 5, and a can be any real value apart from -2. So that notation is all real values apart from -2. And when that is the case, so when m is equal to 5 and a is any value apart from -2, then we'll have no solutions for these simultaneous linear equations. So what about if we had the same question, but now they ask for a unique solution? So I just got the equations there so we can remember what they are. So for unique solutions, firstly we'll look at the gradient. So the gradients have to be now different. So that means m cannot equal 5. And then the plus or minus c, we don't care. So that means when m doesn't equal 5, a can be whatever we want, and we still get a unique solution. So therefore, you can write for a unique solution, this occurs when m is any real number apart from 5. We don't have to, and then you can say, and if this occurs, a can be any real number. So, and a is any real number. So even if a is 0, 10, -5, as long as m is 1, 2, anything but 5, we're going to get a unique solution. And that's because with the unique solution, all we care about is the gradients being different. So lastly, what about if they ask for infinitely many solutions? So infinite solutions. Well, this means both have to be the same. So m must equal 5 and a must equal -2. So therefore, when m is equal to 5 and a is equal to -2, then there's infinitely many solutions. And we can see that because when that occurs, we will get y equals 5x minus 2 and y equals 5x minus 2. So these two are the same.